Hi guys, today I'm going to start going through some practice problems for the integration techniques I talked about last time. Today we're going to go through integration by parts and trig sub, and I'm pulling these problems from the 2020 MIT integration bee. So they're going to be, in some cases, pretty difficult, other cases not so much. Oh, and I want to shout out a channel, I think it's Talk Math, who I put in the description, who already had done these videos, but who helped me to verify that my methodology for some of these was correct. So thanks for that. So first I want to make sure that you've seen this video, or at least you know the integration techniques before we get started. This is basically a guided practice session. Let's just hop into it with that disclaimer. So first you want to do this integral, the natural log of 1 plus x squared dx. And we see immediately that we have a log of a polynomial function. So if we take the derivative of this, we're going to have some kind of polynomial rational function. So we think, what can we do to take derivatives? And we think either Feynman's trick, or we're going to do integration by parts, and there's an indefinite integral here, so we're going to try integration by parts. So the obvious thing is to set u equals to the natural log, because that's what we want to differentiate, and then that means dv is dx, or it's 1 if you like, 1 dx. So then you take the derivative of this, that's x over 1 plus x squared, so 2x over 1 plus x squared, because of chain rule, and integrate this, just x. So this term is x ln of 1 plus x squared minus twice the integral of, so you have 1x and you have 2x from the derivative of x squared. So we can integrate this. And how do we do that? Well, we use the same technique we've done, the u substitution algebra. We do x over 1 plus x squared is 1 minus 1 over 1 plus x squared. And we can integrate each of these. So this one's done, this one is just x, and this one is just arctan. So x ln 1 plus x squared minus 2x plus 2 arctan x, plus a constant which I will be omitting. So next one, natural log 1 plus x over 1 minus x from 0 to 1. So first we want to use the log props to simplify this integral, because this form of 1 plus x over 1 minus x is kind of ugly. So we can do it this way. We could also have done the add subtract trick and say this is negative 2x over 1 minus x. It doesn't really help us too much, so we want to do it this way. So 1 plus x minus 1 minus x. And if you'll recall, we have done this integral before in the video from last time. Integral of x ln of x dx, similar to the one we just did, number 8, is x ln of x minus x. Do it by parts. This is dv. So then we can do two u subs for 1 plus x and 1 minus x. Because the only thing that we'll get as a du is just a sign in this case and nothing in this case. So we can just use this result, apply it to 1 plus x and 1 minus x as kind of this x or u if you like. And then the integral is pretty straightforward. It's just 1 plus x ln 1 plus x minus 1 plus x. And I say ln for ln. So this, because I just plugged in 1 plus x for x, because that's what we have here. And then the 1 minus x similarly in this case. And then we evaluate it. We have 2 ln of 2 minus 2 plus 1 plus 1. And then we have this thing that we have to evaluate. The limit as x tends to 1 of 1 minus x over 1 minus x ln of 1 minus x, which is an indeterminate form since this is infinity, negative infinity specifically, and this is 0. So we use L'Hopital's rule. We write 1 minus x as 1 over 1 minus x. Take derivative of the top and the bottom, and then we say this is negative 1 minus x over 1 minus x squared. Bring this up top, and then it cancels out one of these, or one of these cancels out this, and then just have 1 minus x as x goes to 1 is 0. So our final result, because this cancels these two, is just 2 ln of 2, or ln of 4. So this one is kind of interesting. So we see immediately a very nice u du thing. We have ln's all over the place, and we have a 1 over x, which is the derivative of ln. So we think, let's make the ln of x u, and let's make 1 over x du, right? And then what do we get? We get ln of x times this thing, this integral originally, equals just u ln of u, right? Because this ln out front is just u. This is ln of ln, so it's just ln of u. And then the du covers the 1 over x, so it's just u ln of u du. And of course, we can do this one by parts. So u equals of u, and dv is u. So we could do it the other way around, because we know what the integral of ln is. And then we can just differentiate this, but it's a little bit easier to do it this way. So you have u ln of u equals to u squared ln of u minus u over 2. So pretty simple to evaluate. and that gives you e squared over 4 plus a quarter. You can work through the algebra if you like, but it's pretty straightforward. So there's actually another way to do this, which is kind of cool, so I thought I'd mention it. So actually, if you take a close look at this, you can just integrate this immediately by parts. Because if you take ln of x times ln of x, this whole thing in the numerator, you let that be u, the derivative is actually just ln plus 1 over x, ln of ln plus 1 over x. And then what you see immediately is that if you multiply this by ln, right, which is what you're going to get from integrating 1 over x, you're going to get something very similar to the original integral. In fact, you're just going to get this. This is the boundary term. You're going to get this is actually exactly the original integral, and then this plus 1 term gives you an ln of x over x. But of course, we can integrate this. So what we do is we do the same thing we did in the cosine of x e to the x problem. We just move this over here, put a 2 out in front, and then we just divide by 2, right? So we add this integral to both sides, and then we have 2 of this integral, and then just get 1 of this integral, we divide the whole thing by 2, which is why we have this 1/2. Hopefully that makes sense. It's very similar to the e to the x cosine of x example from the previous video. And then, of course, this integral we can do. This is just, u du, so u squared over 2. And u squared is this, so I just factor it out. Then you plug it in, you get again the same answer. This one also you see immediately a possible substitution, cosine of cosine x, because that's how we're going to deal with this cosine of cosine thing, right? First you want to do this substitution. You want to do sine of 2x equals 2 sine x cos x, which is a very useful one to keep in mind. It comes from the sum of two sines formula. Sum of sine of u plus v formula. And now you do this, you get 2 times this integral, sine x cos x cos x. And now you see, here's your u, here's cosine of u, here's u, and then sine of x is just negative du. So you do this substitution, and now you have just a negative twice the integral of u cos u du, which you just do by parts, right? Straightforward enough to do this by parts, you just kill the u off once. And then you get this as the answer. You have to be a little bit careful because cosine of this is going to be cosine of pi over 2. So you get sine of 1 and cosine of 1, which is weird because we don't usually see those numbers. Okay, and this was one of the harder ones. So arc sine x over x cubed. You might see what we have to do already. There's 2 ways we can think about getting rid of arc sine. One way is we can do some kind of a Feynman's trick or an integration by parts, so we end up taking the derivative of this thing. But it's not the method we've chosen. The other thing you can do is you can do like an x equals to sine of u, and then arc sine of sine will cancel, you'll just be left with u on top. So that's the method we're going to go with. So we want to get rid of this arc sine. We do the u substitution. Then dx, of course, is cosine of u du, because dx du is, And then you have this as your integral. And you can do this pretty straightforwardly, actually, by parts, because we know how to integrate this without the u, right? So if you integrate this, you're just going to get, like, this is just du on top, and this is, I should call it dy or something, because we already have a u. Hasn't stopped me before. But you have a dy on top, and then you have a y cubed on the bottom. So that's just going to be 1 over negative 2 times y to the negative 2. And that's what you get. And then, of course, you still have the u here, so you have to keep it. And you have the integral of derivative cancels this out, so you have negative 1/2 over sine squared of thing, which is cosine squared of thing. And we know the integral of cosine squared, not cosine squared, cosecant squared. And we know the integral of this is just negative cotangent. So this whole thing turns out to u cosecant squared u plus cot u. But how are we going to evaluate this, right? Well, we need to evaluate cot u because, we do know what cosecant squared is because that's just sine, 1 over sine, right? So we know that's just 1 over x squared. This one is not straightforward because we need to evaluate what cosine is. So we have to draw a triangle like this. So a right triangle, right? We know that sine of u is x, so u, take the sine, and that's x. And that side of the triangle is square root of 1 minus x squared. So now we just have this, this thing here. We have this integral we want to evaluate is going to be arc sine for the u, and then 1 over x squared for cosecant squared. And then cot is going to be cosine over sine. So So that's going to be square root of 1 minus x squared over x, which is what we have here. And if you plug in the numbers, you get pretty straightforwardly the answer is a half. So I hope you enjoyed this video, and that's it.